small, and it wasn't a very big warming forcing. But at that same time, we were emitting a lot of smoke from coal plants, all springing up all over the place, and that caused cooling. And that is based on annual. Actually, it's based on weekly amounts of pollution because it lasts in the atmosphere for about a week. And so that was very strong cooling forcing, and that
Yeah,
overwhelmed the relatively weak warming forcing until we got to the 1970s, and then the Clean Air Act and related kinds of policies were passed around the world, and we started cleaning up that pollution. And by that time, the CO2 warming forcing was quite strong because we had put so much CO2 in the atmosphere by that time, and now we have this steady uptick that only gets goes up faster when we clean up more pollution.
Yeah.
And a lot to learn from this graph, in other words.
Yeah, there's also a lot to see indeed. And it's, you can see that until 1980, there wasn't really much warming. It was like a half degree, right? So that's 100 years. Over this 100-year period, there was about half a degree. And then the next half a degree, that was until, 2014. So that's 34 years. And now we have another half degree in, 2014. So that's a little more than 10 years. So,
right. Wow.
Yeah, so that, of course, this clearly shows an acceleration, and of course you can have a long discussion about when acceleration happened and by how much, but I think we'll get to that in a bit, because that also relates to what we can look forward to with 2026. And this is another data set, the ECMWF, the European Weather Agency, global temperature, and it's just relative to 1850 to 1900, and it's very similar. And here you also see that, so the last 3 years were on average 1.5 degrees Celsius above pre-industrial, and even more. And then the peak, so if you take out the hottest months, the hottest months during this El Nino period, it was 1.6 degrees Celsius above pre-industrial levels. So, yeah, I think for all intents and purposes, we've reached now the moment where we are passing 1.5 degrees Celsius of global warming.
And I think we also know that because we just are going through a La Nina cooling period, and it dropped into the 1.4s. And you say, aha, it's below 1.5. But that kind of proves that we are at 1.5, because when you're in La Nina cooling periods, you should be below the trend. And when you're in El Nino warming periods, you should be above the trend. So if we're at 1.6 during El Nino and at 1.4, and actually it's more than that, but in the 1.4s during La Nina, that tells us that we're at 1.5.
And so these are monthly data points.
Right.
So then you have to go back very far to October 1976 to see temperatures that were below the average of the 1850 to 1900. So that, and even during the cooling of about half a degree, or that's maybe a bit less, but during the Pinatubo volcano eruption, so a few tenths of a degree of cooling, you see a blue, here it's blue because it was due to the volcano cooling things down a bit. There's not even 1 month below the pre-industrial temperature. So even with cooling, we won't go. It will be very hard to go back down to these temperatures, which like our grandparents grew up in. And then, I think this is also interesting to see. These are the sea surface temperatures, and then this is for, so you have in yellow 2023, in red 2024, 2024, and then in dark red 2025, and then here you see starting 2026. So of course last year, so if you look at 2024, of course there was a peak of the El Nino, and then it started cooling down, and now this year there was still some sea surface temperature decrease, so cooling of the global average sea surface temperatures, because of the La Nina. So we had a La Nina this year, and I'll get to that in more detail later, because maybe some might question that. But now we are here, and so we're now at like the end of this La Nina period, more or less. And there might well be an El Nino starting. And then if you see the yellow line, 2023, which was, of course, also 1.5 degrees, and it broke many records and surprised many people. Us not so much, because we already predicted acceleration of warming based on the aerosols and the Earth's energy imbalance. But then, so we saw then, but now we see that the temperature of the sea surface temperatures, even during, is it here? Yeah. Even during this La Nina, so this is, what is it, yesterday? So global sea surface temperatures yesterday. Then you see then even during a La Nina, the temperatures are much higher than the yellow in 2023. This is 2023 and this is 2024. So of course you see here's the tropical Pacific. That's when, if you talk about La Nina, we talk about this region, sea surface temperatures in this region, which influence the global climate. So if the sea surface temperatures are lower in this region, we expect lower global temperatures, and vice versa. So here in 2023, we saw, again, there was also a La Nina, but then that turned into an El Nino, of course. But now these temperatures, especially in this region, are even more negative. But the rest of the oceans are, especially outside the tropics, are much warmer than in 2023. Mm-hmm. So that's why I think we could even see a close to, or maybe even a record high temperature this year again. So even breaking not only 2023, but even 2024.
Although Jim Hansen disagrees with that. He thinks that 2026 will not be a record breaker, but because when you have a La Nina or an El Nino, you see the biggest impact in the following year after it forms, which would be this year. And he's predicting, I think, in March or April to have the coolest temperature and then continue going up from then as an El Nino forms. And then, of course, if an El Nino forms this year, later in the year, the biggest impact will be next year. And that's when he was predicting a 1.7 degree temperature for 2027, but not for 2026.
Yeah, I agree mostly with him. And I think there's a chance. There's a chance that we could reach, like, because what happened, of course, in 2023 was that these temperatures started increasing very much. The sea surface temperatures here.
The yellow,
until March,
line.
Mm-hmm. Until March, there wasn't much happening, right? And then all of a sudden, they started spiking up with very fast. So these are anomalies the change from the average for the day. They saw that here in April there were some it reached record highs, but it was still not very extreme. But then in May, it's really started to increase. So you can imagine if we would see another 0.4 of a degree higher than we are here now, then it will be upper somewhere here, right? So and then of course maybe only the sea surface temperatures will be record high, or I think when an El Nino develops, we will definitely see daily record highs again,
Like by the end of 2026, we should be really high.
Like around half of the year, we will start to see again a lot of extreme temperature records breaking. If depending, of course, also on how strong this El Nino is, and it's not just about because of this the variability, right? It's also very much one part. Sorry. Again, this is also natural variability, of course. This is a solar cycle sunspot number progression. So these 11, more or less 11 years solar cycles, and then last year there was the last solar cycle was not very strong if you compare it to the previous peaks. So not a lot of sunspots. But now it's a bit, it's not very strong, but a bit stronger than last time. And that difference is, we talked about the unit watts per square meter on Climate Chat quite a bit, and that means like the global average incoming sunlight is measured in watts per square meters, which is joule per second. So that's averaged over the entire surface of the planet, and then the difference there is about 0.2 of a watt from the low point to the high point, and then about 30% of that is reflected. So the effect is not very strong of the solar cycle. There's not much, but I do think there's that, especially when the energy imbalance is very high. So then we think that this does contribute somewhat to the acceleration of global warming. Because there's more heat input, and then the temperature increases faster. And then also this El Nino. So this is the El Nino index, the ENSO index, the Oceanic Nino index. We're looking at this center part of the tropical Pacific, and I think it's important also to show you this, because of course this was you see this variability since 1995 here. And then here you see the blue line is the Ocean Nino index, and this is the relative index, which is relative to the other tropical oceans at the same latitude. And that why is this much lower here, the relative index? Why is it much lower than the blue one? And also the peak was lower here, and even a bit lower during 2016. For example, compared here you see in 1998, 1997, 1998 is the Super El Nino. Those lines are the same, more or less similar, because how El Nino is calculated, it takes the average of 30 years, and then of the sea surface temperatures, and then the index is the anomaly of the sea surface temperatures over this period. Compared to the period. And we don't know what the sea surface temperatures of the next 15 years are. And even for 2016, we don't know, of course, for that period, even for what the next 15 years are, because we are only in 2026 now. So we need a few more years before we can determine that. So then, of course, these lines will come close together. But then the relative index, why I show you this also to show here is the difference, relative Ocean Nino index minus the Ocean Nino index. So you see, because there's warming also in this region, right?
Right.
So then, if you only look at the ocean, at the normal index, so the Humoshu's, you might miss how strong the El Ninos, or you might overestimate how strong the El Ninos are and underestimate how negative the La Niñas are.
Right.
So again, here is from 2010, the same graph as
I may just say in a different way, just so everyone understands. So in one graph, it's sort of the absolute temperature of the ocean in that particular region relative to a standard from long ago, an average from long ago, versus relative to the current ocean temperatures. And since the entire ocean has warmed up, like kind of everywhere, it has a bigger difference. The cooling might be a certain amount relative to relative to a long ago standard, and not so much compared to recent standard, the recent temperatures.
Yeah, that takes that into account. Yeah.
Yeah.
And that's why I want to show you, is because some might say there was not really a La Nina, because that means that the sea surface temperatures are about half a degree below at this region, below the 30-year average period.
Mm-hmm.
But again, we don't know the next 15 years, so we cannot really rely on that data to see if there's really a La Nina now. And this relative index clearly does show a La Nina over the past 15 months, more or less 15 months.
And we do expect an El Nino in the next year.
Yeah, we do expect this line to go upward again. I don't have it here now, but you can see the heat already accumulating in the like 300 meters below the surface, at this layer of 300 meters. You see that there's anomalous heat, as we call it, accumulating, so the temperatures are relatively warmer, a few 50 meters and lower below the surface. So that you can see that also as a heat battery. So the heat battery is charging now during this La Nina, and also because of these Earth's energy imbalance and this somewhat stronger solar cycle and the peak of the solar cycle. So there's more heat accumulating in this heat battery, and it will come out sooner or later, and potentially this year, which I expect we will see a lot of records breaking again. Whether we will break a new annual temperature, I think that's
for 2027, but it's possible.
It's like rolling dice, and we are, because of this acceleration, and it really depends on how strong this Earth energy imbalance is, and on how strong this El Nino will be, and that's what Jim Hansen wrote in his letter, that it will be a proof of how strong this acceleration really is, and if it's stronger than we think, right, or if it's stronger, I think that's what he showed in this update. He just showed the trend from 2010 to 2025, and then linearly upward. But of course, the acceleration is really started more not in 2010, but in 2015 and after that, right? And especially in 2020, when you have this large desulfurization of the oceans. So if the effect is stronger, which I'll get into it here, I think it might be much stronger even than we feared, right?
For 2026.
Yeah, for 2026. Well, 2026 again, it's just one indicator.
Yeah, of course.
It might go one way or the other, but I think this is the data we have now, and I updated it. I didn't. Please don't read all the. I have to update the writing here, but I just updated some data points, where you can see that the sea surface temperature. These are the forcings. Is this the most updated? Yeah, I think. Yeah, updated. So we have the greenhouse gas forcing, and I will share again in the near future. I will share this, but it's very preliminary, because I was just making this before
you saw it here first, folks.
Sorry,
I'm just telling you saw it here first, folks.
It's hot off the presses.
Off the press.
Yeah. So this, I think that. Yeah, don't pay too much attention on this last dot, right? It's 2024, 2025. It's the greenhouse gas. Oh wait, what happened?
Sorry about that. Sorry about that.
This one.
Yeah, that might be better.
Does that help? Is that clear?
Well, it's good, but it's smaller, so it's harder to read the labels. So, but when
Maybe
we're
like this?
on there, yeah, we can just take ourselves off the labels here for now.
Yeah. So this greenhouse gas forcing is about 4.1 watts per square meters, which is equal to, I think, 573 parts per million CO2 equivalent. So more than a doubling of the CO2 concentration if you convert all the other greenhouse gas forcings. So not the feedbacks. If you convert all the other forcings to CO2, it's like we have already doubled the greenhouse gas forcing. But I hope you all know by now that aerosols cause some negative forcing, so cause some relative cooling. And we don't know, that's the biggest uncertainty in climate science, especially because they impact cloud formation and clouds reflect sunlight. And that's very uncertain. So we don't know exactly how negative it was. But if based on the satellite data, so here we have satellite data. This is NASA satellite data, and you see that this enormous increase in how much sunlight is absorbed. These are 4-year averages to reduce the natural variability. And then you see that there's enormous increase in how much sunlight is absorbed. This is so for the past 4 years, excluding the past 3 months because the data is not in yet, but it just keeps increasing. Earth keeps absorbing more and more sunlight, but it also radiates more heat to space. Even though the greenhouse gases are, of course, increasing and absorbing more infrared radiation, but the energy imbalance is increasing. So the outgoing long-wave radiation, which is a result of increasing temperatures, if a surface gets hotter, it radiates out more heat outwards, and now but it cannot keep up with the increase in absorbed sunlight, of course, because of the greenhouse gases keeping more heat in, and the water vapor feedback also absorbing more infrared radiation. And because of that, the Earth's energy imbalance is still increasing. And so these are, again, 4-year averages. So the past years, it's been really extreme. It's been about 1 watt per square meter higher than at the start of this century. So that means there's much more, more than a doubling, and I think there's quite some consensus about that, because, of course, that's what the data shows. More than a doubling of Earth's energy imbalance, so more than a doubling in how much heat accumulates on planet Earth. And of course, that starts accumulating first at the surface. And that's one reason why I think we could really see very high temperature records again this and next year, so 2026 and 2027.
It's actually more like a tripling since around 2005 of the Earth energy imbalance, and certainly more than maybe a quadrupling since 2000. You don't have the numbers going back to 2000, but you look at the line, it kind of starts at around 2005, and it's maybe 0.5, point something watts.
Yeah, it was 0.4. So we did.
So now it's 1.4. So it's more than a tripling.
Yeah, that's true. And of course, this is just it's like 6 years of data now, right? So it's like and we hope, right? That's hope, and we don't know, but we hope that it will go down again because this aerosol forcing was a one-time thing. So we hope that the level of absorbed sunlight at least will not increase further, because this black line is really crazy, right? It just keeps increasing.
Well, the black line is okay. The black, let's talk
about. It's now
1.9. Regular words for people. So the absorbed solar radiation is how much sunlight basically is reaching the Earth and heating the Earth up. And then that red line going downward, the outgoing long wave, that's the heat radiating away from the Earth. And it's the difference between those two things. How much sunlight we absorb, how much energy we absorb from the sun, versus how much heat or energy we radiate out from the Earth, and the Earth radiates away because it's hot, and hot things radiate out, and that's good. That's good. That keeps us balanced and everything. But now we're not in balance because we're absorbing so much solar radiation. But that absorbed solar radiation is not just because reflectivity from pollution, from aerosols, is dropping as we clean up our pollution, like shipping pollution, but it's also increasing because as the Earth warms, there's less reflective clouds, as we learned from George Salutis in our program about that, NASA researcher who looked at the last 25 years of satellite data looking at clouds and saw there's a trend of reflective cooling clouds decreasing as the Earth warms. So it's a bad feedback effect that as we get warmer, we get less clouds, which makes it even warmer. So to the extent that black line going up is due to less clouds as opposed to less human-made pollution, that's not a good thing.
Yeah, it's uncertain, right? That's really, again, that's the biggest uncertainty in climate science, is what happens to clouds, both because of this cloud condensation from this air pollution, and if you reduce the air pollution, there's less cloud condensation, so less cloud cover, or less white clouds, so less bright, so less reflective. But also warming, there's also less clouds, and of course that's very hard to determine, and it's also in a way it's a bit arbitrary, I think, to most people, and even within the scientific community, it's often like, how do you define a feedback? How do you define a forcing, right? It's because if you run the models, you keep the land temperatures, you let increase, but you keep the sea surface temperatures stable. But then, of course, if you have a forcing that's only focused really over the oceans, you can miss that effect over the oceans, right? Because if the effect over the ocean is stronger, you don't see that if you don't let the oceans warm. So it's also, in a way, it's again about definitions and about how you and when you talk to scientists who study this, you can have a conversation about it. But even some who run these models, who run these simple models, who don't really study it, who don't really understand these details, it's often hard to really have the in-depth conversation about why the models show what they show, or or what's wrong, right? Mm-hmm. Because there's so many variables to include, and if you just run a simple model, you say, yeah, everything's included in the model, so let's just trust the model and hope everything will be all right. Yeah, I think that can be quite dangerous, because then you miss this strong rate of increase which we're now starting to see.
Okay, should I move on to the energy side of things, and or do you have more data?
Yeah, I can talk about all this for hours.
Well, we also have some questions that we'll follow up with.
Yep.
At the end. So let's move to my screen here, and let me get to this. And again, I'm going to remind everyone to please like and subscribe, so we can get more people on the channel. So I'm going to start off with something that's sort of the good news side of things, and this is California Energy for December 27th, which, you remember, it's kind of a rainy time in California right now. And what this is the red line at the top is the total demand for electricity in California. And all of the colors you see here are different forms of either renewable or low carbon energy. So the big yellow spot is solar, and then the green is wind, and then you have geothermal, which we have in California. Not a lot, but it's nice. And then we have there's small hydro you can't see, but there's large hydro, like water power. And then the dark blue is battery power, batteries discharging. This didn't even exist like 5 or 10 years ago. There was zero of that practically. and now it's a very large amount. And you can, and what all the white area is that is energy that is being fulfilled by fossil fuel energy. So as you can see, during the daytime, solar and wind together are more than we need to supply 100% of the electricity. And the part that's above the 100% line, that's charging the batteries, although I don't think all of that is actually shown. And then during the morning and the evenings, you see when the sun isn't shining, there's a lot of fossil fuel energy supplying. But what you can also see is that more and more every year, this blue area is like more than doubling. So you can imagine by the end of the decade that this also, as we're about to see, battery prices are dropping tremendously. You can imagine this filling in 100% of the missing area. And basically you get more solar during the daytime and wind, and that not only supplies all the energy you need, but also charges all the batteries for nighttime and morning. And then this is based on percentage. There's another graph that shows absolute energy, which is a little wavier and everything, but it's the same idea. So bottom line is that even today in California, which is the fourth, fifth, or sixth largest economy in the world all by itself, we're getting a tremendous amount of our energy, 100% of our energy during the day, from renewables and clean energy. And you can see a very clear path to getting 100% renewable energy within 5, certainly no longer than 10 years, by combining batteries with renewable energy. So that's really cool. Speaking of batteries, this is the price of battery pack. So not the cell. You sort of have the cell, the pack, which is like all the batteries in a system, which has cooling and all that kind of stuff. And then you have the system, which would include the electronics for managing and everything like that. But this is the pack level, and this is dollars per kilowatt hour. And back in 2010, that was about $1,500 per kilowatt hour. And today that same number is about $100. So it's basically a 15x reduction in cost in 15 years. And you can see even since 2024, the price has dropped 8%. And by the way, there's news all the time about breakthroughs in costs coming for various kinds of batteries. And this back then were mostly what's called NMC lithium ion batteries. Now they're LFP batteries, which use all abundant materials, iron phosphate and lithium, and they're much safer. They last much longer. They now have batteries that will last longer than the car will last, and that's generally true. And then there's some that will last, like, for example, 1,000,000 miles and that kind of thing. So anyway, the good news is that batteries are getting really, really cheap. So that's the takeaway from this. This really should be the other way around. There we go. And now this is dispatchable power. This is the International Energy Agency. And the thing to know about them is that their predictions are almost always wrong. It's kind of a running joke that all their future predictions about renewable energy greatly underestimate what really happens. And year by year, they keep doing this. But take a look at what this. So this is dispatchable energy. So this is not like variable wind and solar. These are things that you can kind of store and hey, turn this on right now and get it. So you have coal on this side, then you have natural gas, hydro, water, nuclear, bioenergy and geothermal, and battery storage. So if you take your wind and solar and charge your battery, that becomes dispatchable. Now, the thing to notice, and this is the light blue is 2024 power capacity. The dark blue is power capacity based on current policies in the world, current policy scenarios. And then the green is capacity in 2035 based on stated policies. Like, hey, we promise we're going to do even more to cut emissions or something like that. That would be a stated policy, even if it's not in place. And so those are the three scenarios here. So 2024, basically 2024, and then what it's going to be in 2035. And you can totally ignore all the clean, from a climate point of view, you can totally ignore all the clean energy solutions, because clean energy doesn't release CO2. And so it doesn't cause climate change. But then again, it also doesn't stop climate change. It's sort of neutral, which is kind of why we like it. But when you take a look at coal and natural gas, you'll see both of them are predicted to go up. Not a lot, I guess, compared to, what it could be, but it's supposed to be dropping absolutely dramatically in order for us to, fight climate change. And it, again, doesn't matter how much solar you have, doesn't matter how much wind you have. We're going to take a look at that in a moment. But this just tells you that the predictions from the IEA, which, again, the good news is they're almost always wrong. So hopefully they're wrong about this, and then these numbers will actually drop dramatically. But still, the current policies basically are not on track to help us on climate. Now, battery storage, by the way, is just really interesting. Take a look at how much that is predicted to go up. I mean, it's even hard to 0.2 up to 1.5. So, 7 times. My guess is that the reality of this will be much higher than what they're showing. Again, that's where they always underestimate renewables. But the story here is that coal and natural gas are not predicted to go down. I actually hope they actually will in reality, and that IEA is wrong. The next one is LNG. Not talked about too much in the climate context, but LNG is liquefied natural gas. It's a way that you can ship natural gas by a ship, by boat across the world, because it's normally something that you can only put in a pipeline, so you couldn't ship it internationally very well. But now that we've done that, it's very energy intensive to compress and cool natural gas enough to ship it. And of course, natural gas itself is methane, which is 120 times as powerful as CO2 in warming the earth while it's in the atmosphere. The good news, it doesn't stay in the atmosphere near like CO2 does forever. It usually dissipates in about 15 years or so. But what this shows is that we're greatly increasing natural gas, especially in the United States, predicted to increase greatly. And there's also Qatar and Australia in here. But also the point is that this increase in authorization happened under Obama and Biden as well as Trump. And so it's not like, just the pro-fossil fuel president did this. It's like all administrations were for this. And this is really unacceptable stuff if you're going to be fighting climate change. And then in the bottom line for all of this is that here are, again, the IEA. And what they're saying is, based on current policies around the world, they expect CO2 emissions from fossil fuels. These are energy-related CO2 emissions. There's let's get this back here. There we go. There's also energy-related, there's also land use CO2 emissions, like deforestation and things, but these are energy-related. And it's currently about 38 gigatons a year. And what they're saying, under current policies, that's going to stay about the same. But you say, but the good news is that governments have promised to lower their CO2, and said, well, based on those stated policies, it'll drop a little bit down to 30 gigatons. Now, a net zero scenario would have to get us down to zero, obviously, by 2050. And that's this green line, which just ain't happening. And and if you wanted to stay within 1.5, which is not really even theoretically possible, but based on the carbon budgets issued by the IPCC, you would essentially have to have a vertical line down here, like within a few years or something. And that's not going to happen. So the bottom line is that the predictions are, we're not taking climate change seriously. We're not going to be lowering emissions very much. Now, the good news is, going down a little bit is better than going up a lot or a little bit. So yeah, it, relatively speaking, could be better than it could otherwise be, but that's not really the point. The point is that these are lines that get us way over 3 degrees of warming, on the way to 4 or 5 degrees of warming by the end of the century. So that's not acceptable. That's, the game over kinds of stuff. So we have to be changing these predictions. Now, again, the good news is the IEA is almost always wrong tremendously on all their predictions. So this is not etched in stone by any means, and we do have the opportunity to control our future. So I think that's that was sort of the energy side. I want to talk about a little bit about impacts. What are the impacts of climate change today? This is what's happening now. So one thing notice is that there's a lot more flooding, right? And extreme rain seems to be increasing, which it is. And so even the average precipitation could stay the same. Like in the United States, the average precipitation is about the same, but it's getting wetter on the East Coast and drier on the West Coast. But even when it does rain, it's raining more and more. And as this graph shows, so this is on the Northeast US, taking a look at days with 2+ inches of rain, gone up 49%. Excuse me. Sorry about that. And then days with 3 inches of rain went up 62%. Days with 4+ inches of rain went up 84%. And days with 5+ inches of rain have gone up 103%. So as you can see, not only do we get more rain, and that makes sense, as the Earth warms, for every degree Celsius of warming, you get about 7% more water vapor in the atmosphere. So the atmosphere is holding more water. So, okay, we should have more rain, but when the averages go up a little bit, the extremes go up a lot, and that's what we're seeing here. And so this is not just, maybe the news is covering flooding more often. No, it actually is that extreme precipitation is increasing. And that is devastating because our infrastructure is not designed to handle 5+ inches of rain. I mean, it's just, that's the sewer systems and things and drainage systems just can't handle that. And especially when on occasion it goes to 10, 15, 20 inches of rain in 24 hours, which is absolutely insane because 3 inches of rain is an incredible amount of rain. And when you get up, above 5, it's just absolutely crazy. So that's something that we're seeing today. The other thing we're seeing are more heat waves. And so global warming has made heat waves 5 times more likely already than they were. So basically, whenever you have a heat wave, you can be 80% sure that it was due to climate change and not just a naturally occurring heat wave. And in the future, we're going to see them 12 times more likely around 2040. And at that time, you can say, every time you have a heat wave, you can say with more than 90% surety that it's due to climate change, not a natural occurrence. So that's the kind of thing that's already happening, that's going to be increasing over time. And then we haven't even gotten into tipping points and things like that, which we've talked a lot about on the program. So anyway, that's some of the sort of where we are in the energy system and very, very, very high level on climate impacts. So let's get back to Leon. Are you there? Whoop. Well, maybe not. Let's see. Yeah, there he is. Okay.
Sorry, I'm here.
So with that, I want to just keep things moving. Unless you have any comments on what I just put on there, we can bring in Stacy and go through some questions.
No, I think it was a good summary. Indeed, there's a lot going on. We'd also talk about oil a bit more. Maybe there's some
oil. Anything going on in the oil markets? Any current events on that?
I don't know. Maybe let's see tomorrow morning what the markets are saying.
Anyway, let's bring Stacy in. Whoop, sorry about that, Stacy. I hit it twice. Welcome. Well, I can't hear you, Stacy. Yep, you might be on mute.
Sorry. Hi.
There we go.
Happy New Year.
Hi. Happy New Year, Stacy.
Happy New Year.
Yeah, I almost missed part of the this current news cycle because as I might have mentioned to, well, at least Dan, I was in Alaska for a trip, and it was in Fairbanks, which is one of the coldest places on Earth. And of course, I can't stop thinking about climate and bikes, and um, it is, it's hard because it is so cold that they have to do crazy things like, oh, you go to the grocery store, you leave your car running. Because if you don't, it might not work when you're done. They have plugs everywhere to plug in their gas powered cars so that, they're block heaters. They're called engine block heaters, so that the fluids inside of the engine do not freeze in the
Mhm.
30 minutes to an hour that you're there. It was 40 degrees below when we were there. And so I'm here at home now. It is 90 degrees hotter than what I left. And I'm still wearing this. you know. Um, it's there is no wind. There are 4 hours of daylight at this time of year. So it is, I have to question, well, why is Alaska, or let alone Fairbanks? Um, what is the purpose of that place? Um, why would humans live there at all? And the answer is it's oil
Well,
and minerals. But
nowadays,
uh,
there have been
yeah,
people there for thousands of years, but yeah,
indeed,
but a
indeed.
very
And I
different kind of living situation.
Yes, and I learned about Beringia or whatever, or when the Bering Strait was closed and
Hmm.
people walked across, etc.
Beringia.
But it's being somewhere like that. It was very. I did see one person on a bike though, and I ran to the window to
In
take
the
a picture,
winter.
but I couldn't. I was like,
I love you.
like 40 below a zero, and the person is on a bike, so my heart goes out to them
So
in
I read a book
Fairbanks.
long ago called "Going to Extremes" by Joe McGinnis, and it's all about life in Alaska. And the one scene I remember, there was a guy who was walking outside when it was super cold, and he had a bottle of alcohol. I don't know what kind of alcohol it was, maybe whiskey or something like that. And he's walking around with it, and he took a swig of it and instantly died. And the reason he instantly died was because alcohol doesn't freeze like water freezes. And so it was super cold, from it might have been minus 20
Oh,
degrees or Fahrenheit or something like that. And he took a swig and it just instantly froze the inside of his body,
oh my
and he
gosh.
died. So don't do that if you're in
I
Alaska.
did
Keep it
not.
inside your jacket close to you to keep it warm. Okay.
I
Just
did,
advice.
but
We give advice on this channel, so that's some
yes,
advice.
by
Especially
the end
related to climate.
by the end of it, we were getting pretty like, all right, we're not going to wear our 52 layers. It's like I will wear what would be, like a Tahoe or Northeast winter type get up, only one level of gloves, only, all of these, a vest and a jacket, not the other jacket with a jacket on top of it. Um, and I did go in North Pole, Alaska. We were there yesterday, and I did stand outside without gloves at all, which was a big thing.
Mhm.
But yeah, when I'm, I think the thing that and that I kept thinking is, it will never ever ever happen here. If there are people that live in this place, these things will not ever happen or take hold. And so it made me think of the American attitude of, I if they don't do it, well, why should I? Whereas it should be the flip. They can't, so we must. You know what I mean? Like
Okay.
if you have recycling and composting, etc., available to you, you must avail yourselves of it. If electric vehicles are a possibility for you, you must avail. If bicycling, transit, etc., not using a car at all is available to you, you should do it. Because there are people and places that cannot do these things. And so those of us who have access to it, that is a privilege, and we must do it. That was
let's get to
that was
the
my weekend.
questions here, because we have actually quite a few.
Yeah, so I mean, some of them you got to already, talking about what the difference of why Hansen is saying lower. The one Jean-Viet said, I'd like to see more focus on how we know that effective warming is at 1.6 to 1.8 C post aerosol masking, and how once we breach 2, AMOC is expected to breach its tipping points and rapidly collapse.
Well,
those
actually,
numbers
so
right?
let's correct a few things. First of all, without any aerosol masking, in other words, the pollution from shipping, coal plants, etc., that's estimated to be half a degree Celsius to 1 degree of Celsius of cooling. By the
Even
way,
more of the northern hemisphere,
and maybe more if Leon and Johansson are right. But let's call it 1. To pick a number. So that means we're currently right today at around 2.5 degrees of warming without that masking, without that cooling from our own pollution happening. So that's it's not just a few tenths. It's a lot. It's a big number. It's also, by the way, one of the reasons we know that like solar geoengineering using sulfur in the stratosphere will work. One way we know it works is because we're doing it today. We're just doing it very inefficiently and accidentally, but we're still doing it, and we're using 10 times more sulfur than we actually need to do it because we do it so inefficiently. So that's number one. What was the other part of it? Was AMOC. We talked a lot about AMOC on this program. There's a whole playlist if you want to listen to it. So, but I will say a few things. It doesn't just rapidly shut down. What the problem is around 2050 or so, and we don't really know when, but the warning is it could be that soon. We might pass the point of no return for AMOC collapse. And what that means is that the AMOC will start to go down, and over a period of something like 30 to 100 years, it will go down to not to zero, but to a low level. And that would be catastrophic, including while it's on the way down. It doesn't have to be at the very bottom for it to mess up absolutely everything. So, and it's already gone down 15 to maybe 20% already, just from a slowing. And then it's sort of this point, it keeps slowing to a point, and it's self-reinforcing. So once it slows a certain amount, we don't know exactly what that amount is. It just kind of goes on its own, no matter what the hell else we do. Now, there are things we can do to strengthen the AMOC. We did a whole show on how doing solar geoengineering the right way could actually strengthen the AMOC by cooling the Arctic and stuff like that. So, it's not like hopeless necessarily, but of course, in all of these things, we actually have to choose to act. Right now, we're not. We're choosing to fail, but we could someday choose to succeed. And when we do, then we have tools at our disposal that can help address the problem.
Yeah.
The other is now I'm gonna say this, Nadia, but I lost what you were referring to. Maybe you guys will know. How does it, I'm not sure what it is, look with quadratic or higher degree Savitsky-Golay filters with various window sizes? How much does the window size matter?
Oh, I think you're talking about the warming graphs and things like that, and
Probably.
how many
the rate
years
of
back you
warming.
look.
Yeah, I'll show some graphs about that next time, but or maybe I do have them here. Yeah, it's about the rate of warming,
So
and
just a
whether
high
it's
level answer is fine.
or linear. And I think it will, if you look at these, for example, 3 degrees, if we follow a quadratic rate of warming, so if it's not linearly higher, but if it still keeps increasing, we could reach 3 degrees even before 2050. I think that's quite worrying, and I don't think we can really exclude that scenario.
But one thing that happened though was we actually had a step change, right? In forcing, we had all of a sudden, someone flipped a switch in 2020 and turned off a lot of cooling from shipping, and so that's a step change that has an immediate cooling, but it also has a long-term effect because it's a change in forcing happens over 1,000 years, right? You have the initial step, you have about a third of the warming impact in the first 10 years. The next third in the next 100 years, and the last third in about the next 1,000 years. But it's not we hope there aren't any other step changes like that coming up, right? We might. We see obviously more. We do see more warming from greenhouse gases, and of course we could have more Earth feedbacks.
I think this is always good to share. The Earth's surface is, of course, to about 29% land, and most of the Earth is ocean, and the global warming is about 89 or 90%, around 90% ocean warming. So it's mainly global warming. It's mainly ocean warming, right? And then if you reduce this aerosol forcing over the oceans only, right, you reduce it by about 80%. Then this dimming over the main heat sink, where will have a much stronger effect, and we don't know how strong, but it seems. Again, let me go back to this graph quickly. There's a lot. Here it is. If you look at this data, and these are NASA satellite. These are NASA satellite data, right? So billions have been invested in this data, so we better take it seriously. We better look at it, and we better try to understand what it shows. And it shows that there has been an increase in 1.9 watts per square meter globally average. So that's not just over the oceans, that's global in heat uptake, in sunlight absorption. And this increase in outgoing long wave radiation, so more heat leaving the system as infrared, is also very, very strong. But that cannot, again, and I updated it a bit after I showed it half an hour ago, but to show it more clearly, there's really an enormous increase. And we don't know if it will go down or keep going up again, because if these clouds keep disappearing, because the sea surface temperatures keep increasing, it might get worse. Because the data for the past 6 years shows, especially over these regions, over the Northern Hemisphere mid-latitudes, especially over the North Pacific, shows that the imbalance, the net flux, as we call it, over the North Pacific and over the other parts of the Northern Hemisphere mid-latitude keep increasing, not stabilizing. It's not. If you look at that data, which will translate to the warming, it's not leveling off. It's not a step change. It's still increasing. So we should expect the rate of warming over these regions to keep increasing until this data shows that it doesn't, right? That it comes close together again. So, yeah, I think that's important to highlight.
Okay. Let's see. I got some other questions here. By the way, just one, I think, to clarify. Question was the Hansen global temperature value is 1.4 C for 2026. Why so low? Comment on Hansen's temperature.
Didn't you do that one already, though?
No. But the answer to this is that it's not 1.4. Hansen was saying that the temperature will dip to 1.4 in the early part of 2026. In other words, it will come as low, it'll on its path, will get as low as 1.4. But he did not say it would be 1.4 for 2026. And in fact, I don't think he really said what it would be for 2026. His point was that it won't be a peak, but he does have this like range, how low it could be, but he does think that 2027 for sure will be the warmest temperature ever at 1.7 ish. And I want to point out, by the way, that he said it will be 1.7 with a moderate El Nino. So Zeke Hosfather also published his predictions, and he said it would be 1.6 with a moderate, but he said it might be as high as 1.7. But what he was implying was it would be 1.7 if there was a really strong El Nino. So my point is, when 2027 happens and we find out what the number was, if it was 1.7, it was only a moderate El Nino, then Hansen was right and Zeke was wrong. Because again, Zeke was underestimating.
Yeah, and I think there's, we see a lot of shifting of goalposts there. At first they said there was no acceleration. I see another question about that. And then they said, okay, there is acceleration, but not more than the models show. And some still keep their head in the sand and say that there's no acceleration and that the truth is bad enough while they're lying themselves, right? So I think there's, what we did here, like was this from our paper in 2023, and which was published, the preprint we published in 2022, right? We showed already that there was acceleration. Is it? We predicted already that there would be acceleration without these two data points, right? Without and then people were saying that we were crazy and that it wouldn't happen. And now, of course, everyone agrees that there's acceleration. And again, indeed, so to get to the question, so the question was why 1.4 so low? Of course, that's potentially it will dip that low, right? And this is
because of the La Nina. Yeah.
During the La Nina, depending a bit on but I don't think so. I don't think it will go to 1.4 or let alone below 1.4.
Okay.
But that was the point that it won't go much lower than that, which will be an indication. Because of course we already saw most of the La Nina already, right? The impact of the La Nina.
Mm-hmm.
And then, so I don't expect it to go below 1.4, and that's not low. That's very high.
Right.
1.4 degrees Celsius above pre-industrial is very high, even during an El Nino, let alone during a La Nina, right? So that's and then during and then 1.7 they call it high, but so because the El Nino will increase the warming and because of the acceleration, which we talked about in detail.
Okay. So, Stacey, you have other questions to call out there?
Yeah, well, the one I can answer, obsolete, I think anyway, obsolete optics said, doesn't sulfur acidify the rain and oceans? And I would say, well, yes, it all depends on the amounts. I'm assuming it was meant in reference to SRM, and in which case it's all a matter of amounts. And
yeah, so let's talk about that. So putting sulfur in the lower atmosphere from coal plants and ships and things like that, well, especially from coal plants, which are on land, and then it blows, to nearby, that it causes acid rain. That was a big issue in the 1970s in the U.S., and therefore we passed rules and regulations to put sulfur scrubbers on coal plants to prevent that. And of course, one thing that does is it causes heat to go up. Also, Europe did this too, but China didn't. And China was building lots of coal plants, and their sulfur emissions were going way, way up. And you saw the pictures in where you couldn't literally look across the street in Beijing or some other Chinese city. You couldn't see the buildings on the other side because the pollution was so strong. Everyone had to wear a mask and everything. And literally millions of people a year, like estimate 8 million people a year, or 1 in 5 deaths was due to this pollution from burning fossil fuels. But China didn't like that pollution either. So they're putting desulfurization systems on their coal plants and cleaning that up. You can have a whole discussion on that. But the important thing to note, when you put the sulfur in the stratosphere instead of the troposphere where we breathe, you put it way up high, then a couple of things happen. First of all, in the lower atmosphere, that pollution only lasts for about a week before it falls back to the ground. So you have to keep putting more and more up every week in order to have the cooling effect. In the stratosphere, it lasts for a year or so. So you need far, far less of it. Number one, you need far, far less of it to do the cooling you want. But number two, when it falls out eventually, most of it falls out as rain, not as breathable air, so you don't breathe it in. And also 2/3 of it, since it's well spread out by that point, 2/3 of it falls into the ocean because 2/3 of the globe is oceans. So it's not a health problem. It's a far, far smaller health problem if you do it the right way, where you use far less of it way up high versus the way we're accidentally doing it today.
The question was about acidification. And the acidification, right? The main cause of ocean acidification is CO2 emissions.
Carbonic acid is what the other
carbonic
name
acid.
for CO2
40
is.
billion tons per year. And then compare that to 100 or
70 million
now
tons
about 40 million tons of sulfur dioxide.
I think it's 70 million now.
Sorry?
And it would be far, far less for it would be about 5 million tons if we did it in the stratosphere. So
yeah, so it's orders of magnitude less. And of course, it's true. And what a problem is also the scrubbers that wash the sulfur from the exhaust gases if they use these high sulfur fuel oil, like which they make from this country in Latin America, northeast of South America. Maybe you've heard of it. It's called Venezuela, where they make this very high sulfur fuel. They take it from the ground, and now that there's some other country that's going to do that for some reason. I don't know the details, but and so they take this high sulfur fuel. There's I don't know exactly, but I think 10% of the content of the mass of this fuel is sulfur. So you have to take a lot of sulfur from these fuels, right? And then they can use that for other things. But so if they keep the sulfur in the fuel, and they do some desulfurization, then the maximum sulfur fuel content is 3.5%. And then they scrub it from these exhaust gases. So they have these like shower heads in the smokestack, and then they just dump it in the ocean. And then it does contribute more to the acidification of the ocean because it's very concentrated, high concentration. You don't first put it in the air and then it spreads out over the ocean, but you dump it in a very high concentration in the ocean. So and that's really bad for the fish, of course. And I don't want to eat those fish that are in these very high density shipping areas.
So let's do some other quick questions. I just see these. I kind of saved these.
Just as a follow-up, our predicament said SRM does not fix ecological overshoot. Yes, we agree.
What do you say?
SRM does not fix ecological overshoot. Yes, we agree. It is a Band-Aid on top of a gaping wound, and what I think we view as one of the only chances we have, because there is zero willpower to make the changes and get off fossil fuel, which is necessary.
It's not like it has no effect on ecological overshoot. It has a very big effect on ecological overshoot, because part of the ecological overshoot is levels of CO2, which acidify the ocean and destroy shells of fish and things like that, or sea creatures. But first of all, SRM does lower CO2 emissions a lot, because warming causes emissions, right? It's the feedback. And that's why the warming is much more than the CO2 warming, because the CO2 causes warming, which causes more emissions, etc. So when you do cooling, it has the opposite effect. It actually decreases emissions, number one. And number two, a lot of ecological destruction happens from warmer temperatures, drying out forests and causing fires and destroying habitats and killing creatures through heat waves. And look at Australia. I mean, it's just awful there. And so cooling helps. It's not like you snap your fingers and everything is the way it used to be, but it has positive impacts, not only on cooling the earth, but it also has positive impacts on ecological systems. Until we, keep going, if we do that and we keep emitting and we keep doing bad stuff, I mean, of course, it's not going to end well. It might buy us a little bit of time at that point, but if we again decide to succeed, then we will get rid of our emissions. We'll capture our past emissions. We'll cool the earth in the meantime. We'll restore habitats and things like that. We'll see what we end up doing, but the choice is up to us. So anyway, I wanted to cover this one here. Are there architectural concepts or infrastructure in a 2C world by any chance that includes the added precipitation? But perception, but I think I meant precipitation, I think is what it's meant there. And first of all, I have to point out that we're not going to be like rebuilding all cities in the next 20 years to get ready for 2C. So it's not even something that theoretically going to happen. I mean, we'll try to strengthen the infrastructure we have, but the answer is we're not ready. And we're not ready for the precipitation. We're not ready for the heat. We're not ready for the fires. We're not ready for the floods. We're not ready for anything like this. And we're not ready for our food systems, of course, which is one of the really critical things. Here's another, doing some quick ones here. Please, Dan, please see the work of Van Weston, Michael Mann, Tim Lenton, Stefan Ramsdorf, including foundational stability work from Klaus Hasselmann and Carl Wunsch regarding AMOC. Well, first of all, we had Ray and Weston on twice, I think, so far, talking about AMOC. We had Michael Mann on. I do want to invite Tim Lenton, by the way, soon. And then Stefan we've invited. So we've talked, there's a whole playlist on AMOC, so go listen to that. Go listen to Ray. He's a great speaker, by the way. Explains things really well. And I know he does have some new research on AMOC that we want to talk to him about. So yes, we're interested in all those folks. Okay. And Stacey, you have another one? I got a bunch here.
One that I thought was interesting. I don't think the answer is yes yet, but A. Scott asks, is the current low price of oil the result of Chinese electric vehicle growth?
Well, I mean, that's part of it. I mean, everything impacts it, right? And more than 50% of their cars are new cars are electric, and they're on their way to near 100. Norway's at 97% new cars are electric. US is far behind at around 10, but I think California is 20 or 30 or something. Mm-hmm. And so yeah, the trend there is pretty obvious. I think we're near break even. It's already cheaper to own an electric car than it is to own a fossil fuel car when you take into account fuel cost and maintenance. But the upfront price of an electric car is going to be cheaper than a fossil fuel car starting around now. It already is true in China. You get a fantastic new small car for $15,000, that kind of thing, which is a really good car.
This year, BYD overtook Tesla as the world's preeminent
the seller of EVs, yeah, and but the price of batteries, as I pointed out before, is dropping dramatically. Mm-hmm. That's the main cost driver for an EV. Basically, an EV is a box with batteries and a couple of electric motors, and so the batteries get cheaper. Well, and some wheels. You throw in some wheels on the electric motor, and so that it's getting super cheap. It's getting super cheap, and
I think supply is also an important reason, right?
Say again.
I think supply, to get to the question also, supply of oil. There's still a lot of oil, and maybe the economy hasn't grown as much as some thought it would have. And yeah, there's the US, of course, keeps fracking for oil, and
that's right.
We just keep drilling more oil, and even in hard to access places and the dirty stuff. Of course, most of the cleaner, more accessible oils have already been harvested. So now we get more of the high sulfur stuff and more of the polluting, which also takes a lot of energy to take out of the ground. But yeah, demand is there, supply is there, and
but it is
$60 is quite high. $60 is, like, compared to the past decades, $60 per barrel is quite high. It's not, and let's see what it will be tomorrow. I don't know. It might be.
Well, I heard actually about Venezuela being invaded, is that they're not going to be able to get that oil because the price is low, and it's below the cost of production for a lot of these high cost places to extract oil. And so therefore, if they opened up that oil, it would hurt oil companies around the world, including U.S. oil companies. So they're not going to want to really access that oil for a while.
But it was U.S. oil, right?
It's thick oil, so it's going to be like harder.
They stole it, right? They stole 300 million barrels of oil, right?
Of what already from what, Venezuela?
The U.S. No, Venezuela stole 300 million barrels of oil from the United States, if you have to believe Trump.
Oh, you mean because they nationalized their oil companies?
I don't know.
Yeah.
They stole it from I don't know how
that is, by the way, one of the drivers of what really happened here. It's not drug cartels or anything to do with that.
It's oil.
Yeah, it's oil.
I usually don't really try to make sense of what.
And also, as many people pointed out, imagine no one's going to invade your country to take your sunshine and wind. So we have lots and lots of wars over oil all the time. Everything in the Middle East all the time. Here, in this case, clearly about oil. It's kind of hard to imagine someone being invaded to get their wind and sunshine. Although people try to, they'll come after your lithium or something like that, in order to build these things, and which is not really true because these minerals are, first of all, lithium is plentiful around the world, by the way, and also we mine and extract. If you took all the minerals that we need to extract to have 100% wind and solar and renewable energy, that would be about 4 times what we extract today. But even at that level, which is obviously very, quote, very high level, fossil fuel extraction is still 500 times more than that. Mm-hmm. So if we went, another way to put it, if we went to 100% wind and solar, total extraction, mining and fossil fuel extraction, total extraction would drop by over 99%. So when people say, we can never do 100% wind and solar because there would be so much mining going on, remember, the amount of mining will drop 99% when you include fossil fuel mining in that. And as Bill McKibben mentioned on our program, and he's mentioned other times, if you had 100 ships holding oil can be replaced with 1 ship holding solar panels. So if you want a total amount of energy, because remember, the 100 ships, you burn it and it's gone. Mm-hmm. But that 1 ship holding solar panels is going to provide energy for like 30 years, right? So
solar panels or cells, even panels or cells?
Panels, yeah.
Panels.
Yeah, so
it's a lot of air
solar panels versus a ship full of oil.
A lot of air.
Well, no, you pack them in. I'm sure it's by volume, right?
Sorry?
I'm sure they pack them in or by weight or something like that.
That's the point, that you're not shipping like only the solar cells. You're shipping all the, at least, I don't know, I'd like to see the calculation behind it, but like a solar panel, of course, there's a lot of aluminum, glass, air, green, and packaging. So if that's true, that's really remarkable.
No, it is true. I mean, that's why you get this 500-to-1 ratio of minerals mined for renewable energy versus for fossil fuels.
Nadia,
I did the calculation once a couple of years ago. For every 1 ton of lithium that we mine in the world, for every 1 ton of lithium that we mine 50,000 tons of oil and 100,000 tons of coal. So when people say, oh, lithium's this big problem, and first of all, lithium's like one of the most common elements around. We just didn't mine a lot of it because we didn't need it. And now all of a sudden we need it. And surprise, surprise, we find that there's plenty of places to get it, of course, at this point. But anyway, so the scale is off the charts. It's even really hard to imagine the infrastructure involved. Another stat I heard, and I don't remember the exact numbers, I think this came from Bill McKibben. I think 1.3% of the United States is used for ethanol production, and I think it was 1.6% is oil and gas infrastructure land. And you take that together, and if you went to 100% renewable energy, you would like get rid of like something like 3/4 of that. You only need, I know you need only half of the land used for ethanol production to power the entire United States with solar panels. So the land needed for everyone worries, oh, renewable energy uses a lot of land. It would actually use less land than we use for ethanol and oil infrastructure. So,
can I take 2 short questions?
Yeah, go ahead.
Question in the fresh out of the press. I don't know. Radiative. Oh yeah. In fresh out of the press, radiative climate forcing, NASA, a 4-year average was used. Why not a 3-year average? Yeah. I like to use 4-year averages because it reduces for these numbers, because it reduces variability, and because it it accounts for leap years, and also that helps to, if you look at data for different hemispheres, because these values are very high, very large, because you have like 300 watts per square meter in 1 month and a very little over the other month at certain latitudes, right? It really matters how you do the averaging. And then, yeah, because our colleagues at NASA advise to use 4-year averages when looking at different regions. So, yeah, that's one of the reasons I use. I could use any averaging, right? You can. The trend is always the same. Yeah, I also want to say I'm making the data more accessible. It's one of my New Year resolutions, that I want to make the data more accessible, also because of what's happening with all these anthropogenic climate change deniers and taking all these websites offline. I uploaded the data from these NASA data, relative to 1880 to 1920. I uploaded that to my GitHub. I uploaded the data from the Environmental Protection Agency to my GitHub, Leon Simons. You can find it there. So, please do that as well. And I will also upload the data from these NASA satellites in the near future, so you can play with it yourself. You can do some averaging yourself to see. Yeah, and I think that's important to check the numbers and to see if it changes if you do different averaging. And then the second question I want to is this one. After we get past the upcoming El Nino, can we ever expect temperatures to fall back to in line with 2023 levels? And then I go to my presentation, and then this one. So I don't think we will go back to 1.5 of 2023, right? Depends a bit on what you call 2023 levels. Of course, there was an El Nino, and it depends a bit, of course, if we would have a volcano after that. So if you look at that's why I like all these monthly data points, where you can see that this volcano, Mount Pinatubo, erupted in 1991, and then you see that there were some months that were like 0.2 of a degree, or some years that were about 0.2 of a degree lower than the preceding 2 years. And You could improve, look here at when the El Niños were, etc. But yeah, I don't think if the next El Nino is 1.7, and I don't think we will go much below 1.5. Maybe we'll reach
Well,
it.
if you have a La Nina year, or you could have it. It's not. I think the question is, are we ever going to go back to 1.5? I think the answer is no. We could hit 1.5 for a year with a strong La Nina, sure. But you got to remember, a bunch of things are happening. One is we're continuing to pump greenhouse gases into the atmosphere, about 50 billion tons a year. So there's this constant increase in forcing. We're also learning, from Jim Hansen and Leon and others, that the ECS, or the climate sensitivity to increases in greenhouse gas emissions, is more than we thought. And so, for example, that shipping change had a big impact, but its impact is continuing through feedbacks. And until we get to solar radiation management or something like that, where we artificially cool the Earth, or there's a big volcano, we're not going to see an average of 1.5 continue on. In other words, the line is still up and to the right. I think that's the quick answer to that.
Yeah. So here, this is the 2-year average. Again, you could use 3 or 4, but yeah, well, I think the 2023 was the 2-year average. Yeah, depends a bit on indeed how you do your averaging, but the point is clear, right? We could go down a bit. But then the acceleration is real. So we might not go down again to 1.4 even.
Right.
Depending.
Well, next year,
it's always difficult.
It's
always hard to predict the future, right? But yeah,
it's hard to make predictions, especially about the future, I think is the way the line goes. Well, with that, by the way, we're at an hour and a half. There's a lot more questions, but I think we should probably wrap it up. And want to thank everyone for joining us. Let's see. I'm going to be traveling the next couple of weeks, and Leon, you're going to be doing one of the programs. We might have a recorded program for one of them. And also an exciting thing, I'm trying to move all our past video programs onto audio podcasts, and that might happen in the next couple of weeks. So you'll be able to listen while you're driving in your car to Spotify or Apple Podcasts or something like that to listen to our programs that way. And there's a lot of past programs, as we just covered last week. We only did last year's programs, but there's really a few years of programs that you can listen to. And again, if you're interested in AMOC, there's an AMOC playlist. If you're interested in solar geoengineering, there's a solar geoengineering playlist, an accelerated warming playlist, and all of that kind of thing. So you can go check all of that out and listen to a lot more content if you'd like. Want to thank everyone for listening. Again, please like and subscribe so that we can spread this information to others. And anything else, Leon, Stacy?
Thank you for joining, and hope to see more of you this year.
And Happy New Year, everyone.
Yep.
Take care.
Happy New Year.
Happy 2026.